There are more than 5,000 steel wires inside this cable. 221 tons of them failed inspection before they went in. That is the weight of about 150 cars, and nobody ever took it out. It is still up there, holding the road. That is one of 3 things that went wrong on the Brooklyn Bridge. A contractor had been selling this bridge wire that had already failed its inspection and swapping the loads on the way to the site. The chief engineer caught him in 1878 from a window because by then he could not walk. He had gone down into those foundations himself. You have probably heard that the price of this bridge was the men who died down there. At least 21 of them, and probably more. That is true. It is not what nearly brought it down. The reason it is still standing is in the drawings. In 1869, the longest bridge span in the world was about 1,000 feet. John Roebling proposed one that crossed 1,600. Not a bit longer. Half again longer than anything that had ever been built. And he wanted to put it here, over the East River, which is the worst possible place for it. The East River is not a river. It is a saltwater channel with the tide running through it both ways, and it is one of the busiest stretches of water on Earth. You cannot dam it. You cannot block it while you work. You cannot even close it for an afternoon. So the 2 towers that hold the bridge up have to stand in the middle of it. Not beside it. In it. And they have to stand on something solid, which means somebody has to get down to the bottom of the river and build a foundation there. In 1869, nobody had a way to do that. There is one more thing you should know before we go down there. John Roebling never saw a single stone of this bridge laid. In June of that year, he was standing on the ferry slip taking measurements when a boat came in and crushed his foot against the piling. They took his toes off. He refused a doctor after that and treated it himself with water. Tetanus set in. He was dead in 24 days. His son Washington was 32 years old, and the bridge was now his. The answer was an idea about 100 years old that almost nobody had used at this size. Take a box. Turn it upside down, so it is open at the bottom, like a drinking glass held mouth down. Push it into the water. Watch what happens. The water does not fill it. The air trapped inside has nowhere to go, so it holds the water out, and the deeper you push, the harder the water squeezes back. So you pump more air in. Enough air, and the water stops at the rim and stays there. Now put men inside. Give them shovels. They are standing on the bed of the East River, in the dry, digging it away, while the river presses on the outside of the walls and cannot get in. That is a pneumatic caisson. And they built 2 of them, out of timber, the size of a city block. Here is the Brooklyn one in section. You could park 50 city buses on its roof, and the whole thing is made of wood. Now follow it down. Over the men's heads is 15 feet of solid timber. That is squared pine, laid in courses one on top of the next and bolted straight through, and it is that thick because that roof is going to carry a stone tower. Under the timber, the room is 9.5 feet high. A man can stand up in it, with a ceiling above his head thicker than the room is tall. And it is not one room. Walls run across the width and divide it into 6, and those walls are not partitions. They are what is holding the roof up. 2 shafts drop through the timber to take the dug earth out. 2 more bring the men in. On top of those sit the airlocks, and that is the only way in or out of this room. Now come back to the bottom of the drawing, because this is the part people get wrong. There isn't one. There is no floor. The bottom of that box is open riverbed, and the only thing between the men and the East River is air, pushing back exactly as hard as the water pushes in. So how do you get it down? You do not push it. Nothing on Earth in 1870 could push a box that size into a riverbed. You build on top of it instead. As soon as the caisson is floating in place, they start laying the tower on its roof. Granite, block by block, thousands of tons of it. Watch what that does. All that weight presses on the timber. The timber presses on the riverbed. And the rim around the bottom edge of the box is shod in iron and tapered to a blade, so instead of resting on the mud, it cuts into it. The box starts to sink under the weight of the thing being built on top of it. Inside, the men dig the ground out from under the walls. The box drops a few inches. They dig again. It drops again. The tower goes up as the box goes down, and the two of them meet somewhere under the river. Then, just before Christmas of 1870, somebody left a candle in a wooden box nailed to the roof. In compressed air, fire does not smolder. It races. And it went up into 15 feet of dry pine with a stone tower sitting on top of it. Washington Roebling spent 24 hours straight underground fighting it, came up, and said it was out. It was not out. It was eating its way through the roof where nobody could see it. So he did the only thing left. He flooded the caisson, deliberately drowned the chamber his tower was standing on, and hoped the roof would hold. 2.5 days later, they pumped it out. The fire was dead. The bridge was still there. Everything that happened to those men happened because of the door. You cannot just walk out of a room full of squeezed air. Open a hatch and the air blows out, and the river comes in behind it. So the way out is a small iron chamber with a door at each end, and the two doors are never open at the same time. You climb in from below. They shut the door behind you. Then they let the pressure out slowly until the air in the lock matches the air outside, and only then does the top door open. It takes a few minutes. That lock is a beautifully sensible piece of engineering, and it is the most dangerous object on this entire project. Not because of anything it does wrong, because of how fast it does it. The Brooklyn side went well enough. The box stopped at 44.5 feet down, on ground hard enough to build on, and they filled it with concrete and left it there. It is still there. The New York side was the problem. The water was deeper on that side. The ground was softer. And there was no hard bottom anywhere near where they expected one. 60 feet down. 70. The deeper they went, the harder the air had to push, and the harder the air pushed, the worse the men got. At 78.5 feet, 8 floors of building, straight down, under the river, they hit sand and gravel packed so tight it was almost impossible to dig. Not rock. Sand. And Washington Roebling had to decide whether to keep going. Somewhere below him was solid rock, maybe a few feet, maybe 30. To reach it, he would have to work men at pressures that were already killing them. He worked out roughly what it would cost, and the number he came to was about 100 more lives. So he stopped. He stopped in the sand and built a tower on it. Everything on the New York side of this bridge, the granite, the cables, the traffic, all of it, for 140 years, is standing on a judgment call made by a sick man in 1872. It has not measurably moved since. With the towers up, the bridge still had nothing to hang from. For cables had to be made, and you cannot carry a finished cable across a river and lift it into place. It would weigh more than the machinery that lifted it. So they built the cables in midair, out of single wires, one at a time. A wheel ran on a rope from one shore to the other, over the tops of both towers, pulling a loop of steel wire behind it. It reached the far side. A man took the loop off, and the wheel went back for another. 2 wires laid per trip. That is the whole method, and it took 16 months. Men worked that footbridge over open water in every kind of weather, high above the river, on a plank walkway with a rope for a handrail. And every wire that will carried came from one supplier, whose name is going to matter later. When enough wires were lying side by side, they bound them into a bundle called a strand. 19 strands make one cable. More than 5,000 separate wires in each one. Then men rode down the finished cable in little hanging carts and squeezed all 19 strands together with hand clamps until it was round, and wrapped the whole thing in more wire to keep the weather out. 14,000 miles of wire went into this bridge. That is halfway around the world, laid down one loop at a time. The wire for those cables came from a contractor named J. Lloyd Hay. Inspectors went to his mill, tested a batch, and passed it. Then his wagons collected the certificate, made one extra stop on the way to the bridge, and swapped the load. The rejected wire went into the cables carrying the good wire's paperwork, and the good wire went back to the mill to be tested again the following week. And again. It ran for months. By June of 1878, Roebling had established what was happening, and by then 221 tons of failed wire was already spun into the cables. You cannot unspin a cable. So he did the only thing that was left. He added 150 wires to every cable, and he made Hay supply them for nothing. Every account of this bridge treats that as a scandal it survived. Nobody asks the harder question, which is why it was survivable at all. Now, John Roebling had watched a suspension bridge die. In 1854, the bridge at Wheeling, the longest in the world at the time, twisted itself apart in a storm and went into the Ohio River. The deck lifted, rolled over, and tore off its own cables. Roebling read the telegram and said the bridge was not safe against storms. So when he drew this one, he did not trust the cables to do the whole job. Look at what is actually holding this deck. The cables are the first system, and on any other bridge of the period they would have been the only one. Roebling put in a second. He stiffened the deck itself with 6 trusses running the full length of the span, and each one is 33 feet deep, a wall of steel about as tall as a 3-story house, standing on edge the whole way across. A deck that's stiff does not ripple. And then he added a third. Those diagonal wires you can see fanning down from each tower are stays, and every one of them ties the deck directly back to the stone, so the load has a straight path home that does not go through the cables at all. 3 systems. Any one of them a reasonable answer on its own. Now here is the part that is genuinely strange. Engineers went back over this bridge much later and worked out that the stays are not really holding the deck up. The trusses are doing that. The stays, the thing everybody photographs, the thing that makes this bridge look like this bridge, are, structurally speaking, spare. Roebling built 3 because he did not know which one he would turn out to need. That habit is about to save this bridge 3 times over and cover a 4th thing that never came. Back to the men in the box, because by now they are dying and nobody can say why. Here is what was happening. The air we breathe is mostly nitrogen, and your body has no use for it. Under normal pressure, a small amount sits dissolved in your blood, and that is the end of it. Squeeze the air, and more of it dissolves. The harder the squeeze, the more goes in. Spend a shift at 78 feet down, and your blood is carrying several times the nitrogen it was built for. As long as the pressure stays up, none of it is a problem. Now come up the shaft in 5 minutes. The pressure drops, and all that dissolved nitrogen comes back out of solution inside you. It comes out as bubbles. Bubbles in your joints are the pain that folds men in half in the street. Bubbles in your spine are paralysis. Bubbles in the wrong blood vessel kill you. The doctor on the project, Andrew Smith, wrote up 110 serious cases and gave the thing its first name, caisson disease. The men already had a name for it. They called it the bends. The cure was known nowhere. Men blamed it on bad air. Some blamed the cold. Others thought they were simply working too hard. It was none of those. It was the latter. It got Washington Roebling too. He had been going down more often than any of his men, and one day in 1872, he came up too fast and collapsed. He did not die. In some ways, that was worse. He was left partly paralyzed and in constant pain. He could not bear noise. He could not look at bright light. He could not climb a flight of stairs. He never went to the bridge again. He ran it for 11 more years from the window of his apartment in Brooklyn Heights, watching the work through a telescope and writing out instructions by hand. His wife, Emily, carried them to the site. She learned the mathematics of the cables. She learned how much load the steel would take. She learned the whole of it. And when the board moved to replace him in 1882, it was Emily who stood in front of the American Society of Civil Engineers and read out his statement. She was the first woman ever to address them. They backed him, and the trustees let him keep the bridge. So why is the bridge still up? Because of a decision John Roebling made before any of this happened. When he sized those cables, he did not build them strong enough to carry the load. He built them 6 times stronger. 6 times. Put it this way. Fill the bridge, end to end, with everything it was ever meant to carry, all at once. You are using about 1/6 of what those cables can take. Nobody else built like that. And it was not caution. It was an engineer writing down, in advance, that he expected to be wrong about something. He was. 3 things went wrong with this bridge, and every one of them should have been the end of it. The first was the fire. A candle burned 2.5 days inside the roof timber with a stone tower standing on top of it, and the roof held. The second was the ground. The North Tower is standing on sand, and nobody has ever established how far the rock really is beneath it. It has not moved. The third was the wire. 221 tons of it had already failed its own test, about the weight of 150 family cars, buried inside the cables where nobody can reach it. Work the numbers with all of it in place, and the bridge is still 5 times stronger than it needs to be. Washington Roebling's own words were that there was a margin of at least 5, and that he considered that perfectly safe. They added 150 extra wires to each cable and sent Hay the bill. And there is a fourth thing, which never happened at all. Nobody in 1869 could describe what a strong wind does to a flat deck. That understanding was 60 years away. Roebling stiffened this 3 separate ways anyway, and could not have told you which one he was going to need. He was covering a thing nobody could even name yet. That is the whole habit in one decision. It opened on the 24th of May, 1883. 14 years and $15 million against a budget of 5. At least 21 men died building it. And the honest answer is that nobody knows the real number. The records were poor, and a man who went home and died a week later of something no doctor could name did not always get counted. 6 days after it opened, somebody slipped on the steps at the Manhattan end. Somebody screamed. 20,000 people were on the bridge, and none of them were quite sure it would hold. 12 of them were crushed to death in the panic. The bridge was fine. The bridge was always going to be fine. Washington Roebling watched the opening from his window. Emily was among the first to cross it. And the thing worth taking from all of it is not the span, and it is not the towers. It is the room he left himself to be wrong in. The bridge had margin. A fire, the ground, and the wire all went against it, and the margin swallowed all 3. The men who went down into the box had no margin at all. Nobody had worked out that they needed any. 24 years after this bridge opened, they started building the Quebec Bridge, and it was going to beat this span by half again. The numbers came back saying it was already too heavy for itself. The man who could stop the work was 2 days away by post. The men on it kept building. There was no margin in that one at all, and 88 of them found out at the same moment. Like it, subscribe, and you will know when the next one goes up, the next thing that held, or the next thing that did not.